Hello, I'm Dan Boniciolli and welcome to the ChemSkills Podcasts. This is the 14th podcast in the series and the topic of this session is the mass spectrometer. The mass spectrometer is an instrument that measures masses and relative concentrations of atoms and molecules. It's an incredibly powerful tool that has a very high degree of precision, and it has been responsible for the discovery of many isotopes of elements, minerals, and even astrochemicals. The mass spectrometer is composed of four main parts. The, at the start of the mass spectrometer is a section called the ionization region, followed by a series of electric plates called the acceleration region, a strong magnetic field called the deflection region, and at the end of the mass spectrometer is the detection region. Now, we are going to go through each of these main parts in the following slides. So let's begin with ionization. Now, the sample that's being analysed is inserted into the ionisation chamber in the form of vapour, and the vapour fills the chamber. Now, within this chamber, there is a warm electric coil that, as the metal heats up, the electrons become more energetic and they gain enough energy to be pulled away from the coil towards an electric plate on the other side of the mass spectrometer that has a fairly strong positive charge. So as this metal coil warms up, electrons are exuded from it and they rapidly travel through this region of the chamber towards the plate on the other side. In the process, any atoms or molecules that get in the way might be hit by some of these fast-moving electrons, causing the molecule to ionize. Now, exactly how it ionizes is the topic of the next slide. This represents an atom in the ionization chamber. Now, the atom's neutral at this stage, but we know that in the nucleus there are a certain number of protons. In the shells around the atom there are a certain number of electrons. I've only drawn one for simplicity here, but the number of protons and the number of electrons are equal in a neutral atom. Now, this atom, if it happens to fall in the path of a fast-moving electron that's just been released from the warm metal coil and heading towards the strong positive plate on the other side, the collision or bombardment could cause this electron in the atom to be knocked out. Let's have a look at the animation. So here comes the electron, it's knocked out, and what happens is that as a result of losing an electron, let's look at it again, the atom becomes ionized. It becomes a positive ion. One more time, it becomes a positive ion because it's just lost an electron. Now, being a positive ion, it's attracted to the next part of the mass spectrometer, which is called the acceleration chamber. Now, the ions from the ionization chamber are formed over here. They're positively charged. These are a series of negatively charged plates with decreasing voltage as you move through, because we don't want the atoms, the ions rather, continually accelerating. We want them to come out of this third plate with a uniform and constant velocity. The velocity, of course, is proportional to the charge on the ion. Now, the positively charged ions are attracted towards these plates because these plates are negatively charged, and they have a hole in the middle. Most of the ions hit the plates and are absorbed into the mass spectrometer and pass through the circuits of the mass spectrometer, but some of them manage to get through those small holes in the middle of the plates and continue passing through the mass spectrometer, accelerating as they go. Now, when they come out of that final plate, they have a uniform velocity, and that velocity is proportional to the charge on the ion. Now, the next part of the mass spectrometer is the deflection region. In this section, there is a very strong magnetic field that's perpendicular to the path of the ion, shown here by these dotted lines. Now, we know that a moving charge can be affected by a strong magnetic field and cause it to display a turning motion. The principle behind this is that atoms that have atoms or ions rather, that have the greater momentum are less likely to be affected by the external magnetic field. In other words, those atoms that are heavier want to continue on in their path. those atoms that are lighter are affected more by the external magnetic field. So essentially, the deflection part of the mass spectrometer begins to separate the ions on the basis of their mass. Now, assuming all the ions entering this deflection region have exactly the same charge, and that is a single positive charge, then the separation at this point will be entirely due to the mass. The heavier particles will want to keep going, the lighter particles will turn into the walls of the deflection region, and the particles of intermediate mass will bend and continue along down through the mass spectrometer. Now, what happens in the mass spectrometer effectively to differentiate between these particles is that the magnetic field strength is increased gradually. So initially the lighter particles hit the deflection, hit the detection part of the mass spectrometer. As the magnetic field strength is increased, the heavier particles begin to turn more, and then increase further, the really heavy particles begin to turn more. So we end up with a range or a spectrum of particles that hit the end of the machine based on the strength of the magnetic field that's being applied at this point. Now, at the end of the mass spectrometer is a detection device. You can see in this diagram there's an ion stream called ion stream B. These ions are the ions that have just experienced deflection higher up in the mass spectrometer, and they pass through the detectors and hit the electric plate at the end of the detector. Now, that plate is connected to an amplifier because there are not that many particles that hit this plate, and so any signal that is received, any ions that hit that point, the signal must be amplified. So it's connected up to an amplifier. But what happens when the positive ion hits that plate is it draws electrons from the plate. And so as soon as a positive ion hits the plate, electrons are pulled out of the plate, and that creates a very, very slight electric current. And that electric current can then be detected through the electronics and then pass through an amplifier. So as a particle hits the plate, an electric current is experienced, it's amplified, and then projected onto a screen or printed onto a chart. So we end up with a series of charts, a bit like this one here, that show particles that have hit the screen at various magnetic field strengths. And in this diagram, this is a mass spectrum of boron. It shows that when boron passes into a mass spectrometer, that is boron the element, we end up with two regions, two spikes in the spectrum, which means there are two different particles within boron. So in fact, this is illustrating the use of the mass spectrometer to identify isotopes. But as well as that, based on the proportion of boron that is shown in this spectrum, we can calculate the relative atomic weights. So you can see that the most abundant of the isotopes of boron here has an atomic mass of 11, and the least abundant has an atomic mass of 10. Now we can tally up the total abundances as we do here. So when we go back to the screen, if we say that this atomic mass here of 11, there are 100 particles that have an atomic mass of 11, and that means that there are 23 particles that have an atomic mass of 10. This gives us a total of 123 atoms, 23 of which have an atomic mass of 10, 100 of which have an atomic mass of 11, which would give us a total mass of 1,330. But when we divide this by 123, because that was the number of particles, we get an average atomic mass of 10.8. And this is how the relative atomic mass of boron is determined, taking into consideration the relative abundance of each of the common isotopes for boron. And molybdenum is inserted into the mass spectrometer. You get a spectrum that looks a bit like this. So molybdenum has quite a number of naturally occurring isotopes. The relative proportions of each are shown by the heights of these graphs. And furthermore, the mass spectrometer can also be used to deduce the structure, the molecular structure of a compound. Now, when this compound is put into the mass spectrometer, as we saw earlier, electron bombardment can knock out electrons. Well, what can happen to a compound is that the electrons involved in the bond can get knocked out. So that can cause the various bonds in the molecule to break. And what you would end up with are a range of fragments that go through the mass spectrometer, fragments of different mass, of course. They pass through the mass spectrometer and produce a spectrum, a fragmentation spectrum that looks like this. And we can look at this spectrum to analyze and go backwards to analyze and determine the structure of the molecule. So it's an extremely important tool. In the next podcast, I'll show you how the mass spectrums can be analyzed to deduce the structure of a particular molecule. So thank you for listening. I hope that was clear. Please join me for future podcasts. Bye.